All right. Hello, everybody. All right. This is a super exciting day. We're going to talk all about electricity. We're going to go at a pretty fast pace. For those of you guys who have taken the Amber book, and this will be at about the right pace. For some of you guys who haven't, maybe it'll be a little fast, but there's a lot to cover today because this is super complicated stuff. It's actually super complex. Complicated is kind of busy work, but this is actually pretty complex. It's a pretty high level stuff. And so what you want to know, the first thing you want to know is Ohm's law. And Ohm's law says that I times V is equal to W. Now, what is I? I is the amps, V is the volts, and W is the watts. And so amps is actually a unit of measure. The thing I really is talking about is current. So, distance is to miles as current is to amps. And volts is also a unit, but the kind of generic measure is voltage. And watts is a unit of measure, but actually what we're talking about is power. Now, here's the thing. If we can think of amps or current or I, we can think of that as the size of the pipe. So we may have a big pipe, or we may have a little pipe, and it literally is the size of the wire. So a bigger wire holds more amps. And V, voltage, is the amount of pressure of the water, right? So, maybe this is a big pipe, but just with a little bit of pressure. Let me change colors here. There's just a little bit of water coming out. And then maybe this small pipe has a lot of pressure. And so there's about the same amount of water coming out of each one, only one of them is a small pipe with a lot of pressure, and one of them is a big pipe with a little. So we'd say that they have the same watts, the same power, because we can get a power by either having a high I, or high amps or current, or by having a high V, or watts. So in the kind of water world, I is the pipe size, V is the pressure, and indeed, back in the late 1800s, they didn't call it volts or voltage, they called it electrical pressure. So electrical pressure, and W or watts or power, we can say is like the total rate of water, how much water is coming out. All right, so we can bring power. Now, what our equipment needs, what our elevator or our fan or our hair dryer needs, is it needs power. It needs power to make it work. And so we need to be able to deliver that power. Now, what we're going to do to deliver the power is we're going to start at the power plant. So there'll be a power plant, and at least historically, although less and less these days, thankfully, it will burn fossil fuels to heat up water, and it'll take that water and it'll spin it. It'll heat it up so high that it's under extreme pressure, and they'll use that pressure to spin what's called a turbine, and that turbine generates electricity, kind of in the same way that rubbing a balloon on your head generates electricity, just spinning round and round and round and making electricity. And what we're going to do is we're going to have some equipment that's going to called a transformer, and that transformer is going to take the power and it's going to send it over the wires. It's going to send it over the wires, and it's going to send it at, we'll call it 100,000 volts. It varies, but very high voltage. And then we can't plug in our hair dryer or touch our elevator button if it itself is connected to 100,000 volts. And the reason is because of this, because of all that pressure. And so there will be lightning from the button, from the elevator button, if we had 100,000 volts. It is way too much pressure. I know you probably have thought of things as conductors or insulators from an electrical point of view, like wood is a good insulator and metal is a good conductor. It's true. Wood's a good insulator, metal is a good conductor, air is a good insulator, but lightning has enough voltage that it can jump across air. So what we don't want is we don't want a situation where we have something that can jump across something it really doesn't, it really has no business jumping across. So we're going to send the voltage, really, really high voltage power around the country. And there's all this kind of equipment. So we're going to talk about, everything from the plug and to the transformer, to the electrical panel, to the kind of giant erector set power lines. And the power is going to go around the country really high off the ground, because there's so much power, there's so much voltage that if we ran these things on normal wooden poles with all that voltage, with 100,000 volts, we'd have lightning hitting the ground right from the wire. And so we don't want that. We got to get them way off the ground and really far apart from each other as well, because we want to make sure that we don't have arcs going across. We want to make sure that fire trucks that have their ladder up don't happen to come near them, that kind of thing. So we're gonna send them around the country, and we're gonna the kind of transformer we're gonna use to step up the power at the power plant. The kind of this thing right here, that thing right there, is going to be a really big transformer, because it's taking 100,000. I used 100,000. It could be as much as 300,000-400,000 volts. And we can send that over long distances. But so it's always this interplay over between, on the one hand, we want to send power over long distances, and that requires high voltage. I'll tell you a little bit more in a minute why. And on the other hand, we want to run our equipment at relatively low voltages because of safety, because of fear of electrocution. So there's this balance. So we're gonna run it under high pressure, because we don't want to come near it. Because again, if we had 11,000 volts, 100,000 volts, we would have lightning from the socket every time you couldn't get anywhere near this. You couldn't even get near enough to take this photo, because 100,000 volts would easily jump across and get you and kill you. So we use this idea of a transformer. Now, a transformer, not going to get into how it works for now. And if you want to ask me about it later, if we have time, I'll explain it. But for now, just say it's magic, right? It changes the voltage. It changes the voltage. So we can do a small pipe with high volts, or we can do a big pipe with low volts. And either way, and not literally a pipe, of course, a wire. And either way, we can bring the same amount of power, because that's what we want to do. We want to provide power. At this stage, we're talking about providing power to your town or to your region. And so then we're going to send it through another transformer that's going to step the power down. We'll call it to 10,000 volts. And at 10,000 volts, we can run it on these kind of power lines, kind of normative wooden power lines that are way off the ground, but nothing like the ones I showed you before. And so we're getting still very unsafe, but much safer. And we're going to run it around your neighborhood in these. So let's draw some more of that in the diagram. So there'll be we'll have another transformer. And that other transformer will step it down for your neighborhood to 10,000 volts. All right, good. Now, that's still way too much to run into our homes. And so what's going to happen is on the power line, itself, sometimes it could be in the ground for an underground line. It could be next to a building, also for an underground line. So it could be sitting on a pad next to a building. We'll take a look at them in a second. We're going to step it down again. And for residential, because this particular diagram I showed you is for multifamily residential, we're going to step it down again till it gets to 120 volts. So let's take a look at what that looks like. So we have, that's what this thing is here, this drum transformer. The transformer, remember, it changes the voltage. So it's stepping it down from, call it 10,000 volts to 120 volts for our house. And you see these kind of up in the air sometimes. Sometimes you see it next to a building on a pad. It's usually this kind of transformer green. Here, this guy's kind of stepping on one. And the transformer itself doesn't always have to be outside. This is this is a photo I took last month. We are inside. So we're inside a building here on Virginia Tech's campus. And there's a door, and this door, I've never even met anyone who has a key to this door. And the reason I haven't is because they don't want anyone, they don't want muggles to have a key to this door. That would not be a good thing. They only want people who know what they're doing to have a key to the door. So why is that? Because there is so much voltage. There is, in this case, 12,470 volts. So it's this level here, what I call 10,000, but it varies. It's this level here is way too dangerous just to let like a janitor have a key. You would need to have basically the electric company has a key, because something like this is in here. Now, here's my question for you. What is in these fins? What is in these fins? Go ahead and put it in the chat. They release heat and they use a coolant, but the coolant they use is oil, because shockingly, oil is not a conductor, which is nuts because it feels like oil should be a conductor because water is a conductor and they're both liquids, but oil is not a conductor of electricity. So we use fins to keep the thing cool because transformers heat up a bit and we want to keep them cool. And so we'll use oil. Now, the reason that this door right here has this sign on it. This is the sign that's on the door. So why is the door off the ground? This is like an IQ test. Why is the door off the ground? Why do I have to step over a curb to get into it? It's not for water. It's not for flood. It's for oil leaks. Eric said it. It's for oil leaks, because there may be an oil leak one day from those fins, and then the oil will be a mess, and we don't want it oozing out. We want to contain it. We don't want it oozing out everywhere. Now, in most bigger buildings, which are the type of buildings that frankly would have an interior, an indoor transformer, in most bigger buildings, these transformers, because of fire code, many bigger buildings aren't allowed to, there may be type 1A or type 1B or type 2A, some kind of a less combustible construction type. And as such, if you had a hospital, we wouldn't want flammable oil to be in the basement of the hospital, because if it caught fire, it takes a long time to get people evacuated from a hospital. So we want to have something that's a little bit less flammable. So there are more expensive chemicals that can replace the oil. But either way, we still want the curb, and we don't. Sometimes we can have oil. It just depends. So anyhow, why would we want to put the transformer inside? Because they're ugly. Nobody, it's amazing how often we just put up with these. Like, we're like, oh yeah, like this is fine. This is part of my building. Like, I cannot remember the last time I saw a Pritzker winning architect have a photo that included this. Why not? Well, it could be because they put it indoors. It could be because they carefully identified where they were going to have things like this and then hid it away, so it wouldn't be visible from most places. It could be because they selectively chose where they were going to take the photo from, or it could be because they photoshopped it out, because that happens all the time. If you're willing to admit it, put in the chat if you've ever photoshopped out like an exit sign or something like that for a photograph, either for a client or for your website or for a competition. So you guys are all saying yes. So it happens all the time. But wouldn't it be better if we could Photoshop these things out before they were even put in, so they wouldn't, not only would they not be there in the photo, but they actually wouldn't be there in reality. Of course, sometimes it costs money. So in this case, it costs money to put it indoors because, well, you have to, well, you understand why it would cost money. Now, so we have something 120 volts. Now 120 volts is something like 75 times as much electricity as it would take to kill you if you were like, in a bathtub and well grounded. But in most situations, it doesn't have enough voltage that it's gonna jump out of the socket and get you. And sometimes it does, but If it does, it's not going to typically hurt you too bad. Again, unless you have a toaster in the bathtub or something like that. Obviously, do not do that. You guys know that. But so when if you think about like a battery, like a 9-volt battery, for instance, in a 9-volt battery, you can touch both poles with your fingers, but it can still your 9-volt battery can still run your remote control. It has enough power to run your remote control. It has enough voltage to run across the wires in your remote control, but it doesn't have enough voltage to run across your finger. Now, if you lick your finger, if you put it on your tongue, if you have a 9-volt battery and you put it on your tongue right now, it will absolutely give you a shock. So if you have one nearby, try it. It'll hurt, but then you'll say you did it. Or maybe you won't. Maybe it's probably better not to say you did. Just not tell anyone you did it. But if you feel up to it, you can take a chance and stick your tongue out. And you know what? You should have someone film you do it too, because even if you think you're going to be a badass, you're going to be scared as it gets close, because it does hurt. Anyhow, Tyler, most of you guys, many of you guys know this, but many of you don't, because I haven't mentioned it in a while. Tyler, who runs our firm licenses here at Amber Book, but also like everyone who does customer service at Amber Book is also an expert, right? So everyone who does customer service, but Tyler, just about is an architect, or has taken the exams, or has already taken the exams, or at least graduated from architecture school. Tyler is a practicing attorney. And so Tyler wrote on the chat, don't try this at home. But Tyler's practicing attorney. And the reason we want to hire an attorney here is because there's a lot of content on contracts and the law, construction law. And so we want lawyers. And then so if you have a question and you write to us or you call us, you will either get me, because I put my phone number's on the website, or you will get Tyler, or you will get Elise or Matt or Tom or Ralph, and they're all architects. They've all taken the exams and finished them, or are taking the exams now. So anyhow, so we have, so Tyler's saying, don't try this at home, which probably makes good sense. So anyhow, we have 120 volts, and we want to get to the plug, right? Our goal is to get to the plug. But before we get to the plug, we're going to have to do a few more things. And one of the things we're going to do is we're going to send our power through a series of panels. Some of the panels are pretty big sometimes. Sometimes the panels are actually quite small. Now, why do we want a series of panels? What could possibly give us a reason to have a bunch of panels before we get to the oops. I'm going to keep consistent now. Oops. All right, a bunch of panels, and then we're going to run our power from one of the panels. Eventually, it's going to go to the electrical receptacle. So go ahead and continue to put on the chat why you think we need panels. And some people said, oh, we need it for breakers, like electrical breakers. Yeah. And we need it for distributions. Yeah. And we need it for lots of circuits. Yeah. We have to kind of use it to branch out into a bunch of circuits. And we need it for meters. And yeah, you got the right idea, right? So what do those panels look like? Well, in your building, well, these are all panels, right? So this is a main distribution panel right here. And so it has a switch on it, and it's where the power, right on the other side of this wall, is that really expensive, difficult to get to transformer. So it comes on the other side of the wall, the power comes in at 12,000 some volts, but then it comes out at a much lower voltage. I'm not going to get into that because that's a whole nother, the exact voltage it comes out at is actually the topic of a whole nother 40 minutes of competence, which maybe we'll do next week or the week after or something. But it's going to come through the wall, and it's going to at a much lower voltage. In this case, it happens to be 480. Don't worry about that too much yet, although that is very important for the exam. But it's going to come out at 480 in this particular building, and then it's going to go into these guys, which are panels also, but this is called switchgear, and it's got a big lever. It's got a big lever. Now, why do we need a big lever on the outside? Why not just have a switch like we do in a regular, like if we have a, why not have a switch like that? Or at least a switch like these guys, where it's a kind of a normative breaker. Why don't we have a Why can't we just put a switch, a regular switch? Why do we have to have a big lever outside? Yeah, I mean, it's too close. We need a physical disconnect, but we don't want to put our fingers near, all that power. There's so much power in these equipment that, the switch I showed you a second ago, the one you use to turn on the light in the room you're on right now, that's different. That only has 120 volts going through it, or maybe 277. Another discussion for another day. But it has 120 or 277 volts going through it. There's no reason to think that it's going to hurt you just because you got close to it. And likewise, in your breaker, the switch that is your breaker, because your breaker is just a bunch of switches. The breaker is just a situation where your finger is very close to the wire. Now, if we have 4,000 or 5,000 watts coming through, we have a lot of power. Well, that can jump out and get us. We don't want to have our fingers that close. And especially if we need to turn off the power and we're a fireman and it's dark and this whole room is flooded because we've been hosing down the fire and I need to come in there and turn off the power. I do not want to be standing in water and fumbling around in the dark in a place I've never been, looking for a switch to turn it off, because I will almost surely get killed. And so we don't want that. So we give them, it's kind of the, those of you guys who are old enough to remember Jersey Shore, the TV show, there was a character on it who said he had a shirt before the shirt. I forgot what the character's name, but someone will put it on the chat. But he would talk, and someone said, "Are you wearing that shirt out tonight?" He said, "No." Mike, he said, "This is the shirt." No, he said, "This is the shirt before the shirt." And so this is a switch before the switch. So the switch you're looking at on the outside of the equipment actually controls the switches inside the equipment. That way, we don't have to get too close to the equipment. So one reason we want to have a panel is to have a switch, and one reason we want to have a panel is just to have a place to distribute it. Because, and that's probably the main reason, is we just need a place to distribute it. We don't want to like have a bunch of wires in the wall that kind of branch out, and then if you ever have to do maintenance or add a piece of equipment to this building, because this building happens to be a lab building, so maybe there's a researcher who gets a grant to study, I don't know, coal dust and the effect on lungs, and they need a special piece of equipment to simulate lungs, and that equipment needs a special power line going to it. We don't want to break down this wall and start fishing for maybe what's the right power to tap into. So it's a node, it's a place for power to come in and then branch off to go somewhere else, where later on, if we want to control it for maintenance or for upgrades, or for anything really, we can just kind of pull this panel off. Well, we shut down the power first, but we pull this panel off. Now, this guy right here is actually a transformer. It's a micro transformer taking that 480 volt power that is coming into the room, and it is it's kicking it out at 120 volts. So it's coming in at 480. And then it's coming out at 120, because we need the 480 to make our big machines work, our big elevators and our big motors. But we want the 120 so that we can still plug in our toaster and the things that we're going to get our fingers close to. So this is called a micro transformer. So, excuse me. Sometimes we have the transformers up on the pole. Sometimes, like I said, we have drum transformers, like we saw, and these will step down the power. These are different panels. So this is a kind of panel that might be at a really big chiller plant or something like that. This is one that might be this is actually probably at a substation. So it's where there's, the substation others. If you drive around your city, you will see a dozen, depending on the size of your city, you'll see a dozen little areas around your city scattered about that are gravel, and they're kind of painted gray or green, and they have a bunch of electrical equipment in them. And they're about the size of, anywhere between the size of the area of a football field to the area of a quarter of a football field, something like that. And that's where you're stepping down the voltage to go into the neighborhood. So that's when we're going from 100,000 volts to 10,000 volts. That's when we're going from the erector set voltage to the regular tree telephone pole voltage. And there needs to be equipment there too, because they have to be able to shut things down for maintenance or monitor how much power is going through a particular wire and so forth. So these are all panels just next to each other. There's all kinds of different reasons for panels, different kind of switches. This panel right here, those of you guys who were here a couple of weeks ago when we talked about the air handling unit, This panel right there is the one that controls that air handling unit, big honking air handling unit that serves a giant campus building. And so so there's if we ever wanted to do maintenance on that unit, we could turn off the power right here. Or if in 20 years we have to replace that unit and we need a different set of wiring, we can hook the new wiring up right here. So it just gives us kind of a place of some real estate. And these are all other panels for other equipment in this lab building. And if you were to pull off the cover of the panels, you would see something like this. So it's like a giant, I don't know, it's like an old-fashioned operator where they would, where the people would plug in the cords to make a connection between you and someone else you were calling. So if you kind of look behind here, and I'm not allowed to go back here. They told me, just stay up here, please. They didn't want me bringing a bunch of students back there because students have backpacks and backpacks to snag on things. But behind there, there's just a bunch of ways to make connections. That's what we're looking at in all these things. So, and this panel is a panel for a breaker box. And so what's happening here is well, actually, before we get to here, let's go and continue our diagram. All right, let's continue our diagram. So we have 120 volt coming here. And what's going to happen is the power is coming in. The orange is what's called a hot line, but we'll make the green line our neutral. Now, the neutral is grounded, but it is not the ground wire. That's a third wire, which is super confusing to people. And again, the topic of another 40 minutes of competence. So the neutral is going to come back through the other pole in each of these panels. Each of these panels has two poles, one for the hot wire and one for the neutral. It's going to go back into the transformer, and then the transformer is somewhere either on the ground or has a wire to the ground, and the neutral is going to go into the ground. And so what's happening is because it's alternating current, we have the current, the electrons, the free electrons moving across. I don't want to, well, maybe I'll just do it on here. We have it moving across this way, going through our appliance, and then coming back this way and going into the ground. That's right, it goes into the ground. But then we're going to yank it back. So the power plant's going to yank it back the other way. That's what alternating current is. So 60 times per second, we're going to send the electron down and we're going to yank it back. And each time we're going to use the ground as like a giant reservoir of electrons. So we're going to send it to and from 60 times per second. Now in Europe or parts of the Middle East, it's 50 times per second. That's why your plugger doesn't usually work in Europe. Although more and more we're getting better at making things that work in both. And the reason that we use alternating current is because in the 1800s, and really even still today, but especially in the 1800s, early 1900s, when we were laying out the whole system, we could not use transformers to step down or step up the voltage in direct current. Let me say that again. Direct current back then, especially, we had no way of stepping up or stepping down the voltage. Now, if you have, what happens is if we send, well, let me ask you, you guys can put it on the chat. If instead of sending out everything, at 100,000 volts, why not just send it all out at 120 volts? Just electrify the whole country at 120 volts. Why can't we do that? Yeah, first of all, we need way too big wires, right? Because the pipes would have to be bigger to get the same amount of power to your neighborhood, to your region, to your state. We would need such big pipes that the wires would have to have diameters that were, the diameter of a small grocery store or something hanging between the wires. So that doesn't make any sense. We can't have that. But the other reason is because we lose power along the way when we send it long distances at lower voltages, and it heats up. It gets really hot. So we had to use alternating current because that gave us a way to get this the pollution associated with burning fossil fuels for power, we wanted to get that the hell away from where people live. Now, of course, it all floats back anyway, and now we have a carbon situation, but we wanted to get the power plant as far away as reasonable, as practicable from the end users, because those people don't want to breathe the nitrous oxide and sulfur dioxide and particulates that come out of a power plant related to the burning of fossil fuels. Nor does anyone want to live next to one of these things just because they're unsightly and they're dangerous and you know, yuck. So so that is why we use alternating current. That's why we did anyway. Now we can step up and step down direct current, but I think actually the way we do that is we transform it into alternating current first. It's actually called inverting it. We invert it into alternating current first. Then we use a transformer to step it up or step it down. And then we use what's called a rectifier to send it back to direct current. So even now, as far as I know, we have to turn it into AC current to step it up or down, but we can pretty easily now go between AC current and DC current in a way that we couldn't before at the scale. Anyhow, so that's alternating current. Now, what happens if I take a wire and I merge it with the hot wire and I run it into the ground? What happens if I do that? Or what happens if I take, or better yet, what happens if I take a wire that's on the hot side and I just join it with the neutral side? Because these wires come together, right? They look like, you know, if I zoomed in 1,000,000 times, or not 1,000,000, but 100 times, they kind of look like this in section. If you cut a wire, so they're actually pretty close to each other. So what happens if I take a nail to hang a picture and that nail happens to go straight across both wires, and now the electrons are moving straight from the hot wire to the neutral wire? What happens? It's a short circuit, it's a spark, and it heats up. So the way that these breakers work, the way that these breakers work is there's a piece of equipment, and the breakers themselves are just a switch. And this switch is just something that if it gets really hot, it automatically, a spring kind of mechanically sends it across the other way. So if it gets hot, it will disconnect the wire. And that's really what a switch is. If you have a wire that's going from left to right, a switch is just a little thing like this that that goes like that. And when you flip the switch, you're basically just mechanically moving a little metal plate from here to here, and then it continues the circuit. So we need a circuit. We need a place for the electrons to go. We can't have a dead end. The electrons don't, I mean, we can. That just means everything's off. But everything has to flow through. It's all kind of magic, and it's really remarkable that we did this for ourselves. We made this entire system so that I can be talking to you right now. It's pretty remarkable. And not so I can talk to you about electricity, so I can physically be talking to you on my piece of equipment, and you can be hearing me and watching me on your piece of equipment. So when we flip this switch, we're mechanically moving a plate behind it that takes the that connects the circuit and sends the electrons on their way, and they're eventually going to go to the ground through the neutral. But that is not the ground. That is not the ground wire. All right. And like I said, that's a topic for another 40 minutes of competence. All right. So then, so we use a panel then for safety, for overcurrent protection, for maintenance, for future upgrades, for distribution. We use it for the meter if we want to send it out to the meter. So now let's look at our question. Where is the equipment that regulates the inverter, translating direct current into alternating current? Well, let's follow the electricity on this particular one. And by the way, we have a record. We've never had 312 people on a 40 minutes of competence before. That's pretty cool. In part because we didn't know it, but our Zoom account shut us off at 300 last time it got this high. So now we're at 300. All right. So let's see what we got. We have from the utility company lines, coordinate with, okay, so we have it coming in. And so we have it coming in this way. And then it says pad mounted transformer, pad and ground by electrical company, transformer furnished and set by final connections by utility company. Okay. And then we have single phase. So it's going to come out as single phase from this transformer. And it's going to go into our building, but still, we're still new service lateral, 5-inch conduit with pole wires by electrical company, conductors by utility company. So we're still doing it by the utility company. That's often underground these days because we prefer to bury our power, but it's also often overground too. I mean, it's more expensive underground, but it looks cleaner and maybe a bit safer. But the utility company, I think right up to the right up until the building is gonna run the wires and maintain the equipment. That's what you're paying your bills for in part. And then it's gonna go through these panels. So each one of these, let me get different colors here. Each one of these is a different panel. And sometimes they're in the same room. In this diagram, sometimes they're in the same room. And sometimes they're in different rooms. And sometimes they're in different buildings. And sometimes they're in the same buildings. That's the beauty of a diagram. You don't necessarily have to show anything you don't want to show. But there's all these different panels. And we have to figure out what these panels are for. Now take a second now to see if you can figure out what these panels are for, best you can, what each one is for, given that we talked about them being for splitting up the wires into a bunch of smaller wires and for overcurrent protection, for making sure there's not a short, and for metering and so forth. See if you can figure out what each of these panels is for. Now, a panel may do multiple things as well. And actually, these are all.
Michael accidentally cut you off just now. Michael.
Okay. Oh, gotcha. All right. So let's see. Where did I leave off?
It's just like 5 seconds ago.
Okay. So we're trying to figure out what these panels are for. So put them. You're doing a great job putting them in the chat. So put them in the chat. What do you think these panels are for? And then there are these panels too. There's just a bunch of panels. And this is for multifamily housing, a typical apartment, it says here. And so what's happening is this power is coming in and we're going to meter it. The utility is going to meter it because they're going to charge, well, they just want to meter it. They want to know what to charge the whole community. But these days, you pretty much usually have to charge the end user. Why is it law almost everywhere that I know of that for new construction, although definitely not in older construction, for new construction, each user needs their own meter. Why would that be? It's for energy conservation, because have you ever, you could just charge everyone the same amount for the bill, you could split it up, but have you ever, been to a bar when everyone knows it's going to be split evenly at the end? Like everyone drinks more because they know that some of their drinks are going to be covered by everyone else, but that's not really why they do it. I don't think they do it because they're selfish. I think they do it because there's a sense of fairness, right? Well, shit, if they're going to be, the person across from me just keeps ordering really expensive drinks, so I'm paying for their drinks. So that's not fair. So I'm going to get some nice drinks too. And so you wind up with that. Or those of you guys who don't drink know how frustrating it is when everyone else is drinking and you wind up having to pay for them. So it's a tragedy of the commons. So what we do, and I think it's in the electrical code, it's certainly the rule almost everywhere I know of, for new construction, is we have to meter each tenant, because that way each tenant is rewarded for conserving electricity, and it's not a race to the bottom where everyone's using more and more electricity because they think everyone else is. All right, so we have a meter there. This is new 2-inch conduit with metering conductors by electrical company. So this is still in the world of the electrical company, and this particular panel right here, this one here, let's follow it. It says incoming line and metering section. So it's a panel just to send the, just to kind of say we're coming in. So if ever we had wanted to, again, split it off there because we were going to do an addition to the building, for instance, or if we ever need to repair something in the whole building or shut it off for the whole complex, it is for the whole complex. We wanted to shut it off for the whole complex, the apartment complex, we would want to do it there. And then we're going to go, and then the electricity is going to go to the next panel. And this next panel, we can kind of follow it up here. And it says solar photovoltaic tap section, dedicated vertical section. So this is where the photovoltaic panels, either currently in place or someone's being proactive and thinking about photovoltaics in the future. The photovoltaic panels are going to generate their power, and they're going to, what they're going to actually do is they're going to run the meter backward typically. So the meter is going to run forward for all the time you turn on the dishwasher or whatever. Anytime you use an appliance, the meter is going to run forward. But if we're producing more power at any given moment than we're using, the meter will run backward and the power will go back to the electrical company. It's called net metering. And that's what this panel does, this solar PV tap section. That's what this panel does. It's going to take in the line from the photovoltaics and give us a place where if we ever replace the photovoltaics or add more or whatever, we'll have a panel instead of, you know, busting open a wall and trying to figure out what's going on. So what we're trying to, what these panels are trying to solve for is we don't want a situation like this. We don't want to just have all these connections in the wall where we have to just use wire nuts to just do that kind of thing. That would be a stupid way to make a building in the long term. We want something clean and neat like this when you open that power panel, so that in the future we can know what it is we're connecting to. We don't have to disconnect each one and say, you know, has the light gone off now? What about now? We don't want that. All right. So, oops, no, one more. All right. So then we have our main breaker. And so it could be separate, or it says it could be in the distribution section, which is this next one. So you could buy one panel that is both for breakers and for distribution, or you could have one that has a main breaker and then downstream of that have one that has distribution. So anyhow, then it's going to go out to a typical apartment and it's going to do this. You know, if this apartment complex maybe has 40 different apartments, so it's going to go to, it's going to do that 40 different times. It's going to go to the apartment itself, which has 100 watt service, two poles, so a hot and a neutral. And each apartment is going to have its own meter also connected to it, so we can charge people. Now, there's also, let me change colors here. We're also going to go to a house panel, and the house panel is for that particular apartment building. So there may be, emergency lights on that apartment building, or a trash compactor for everyone in the building, or just the electrical receptacles in the hallway of that building that are going to feed the vacuum cleaner when the maintenance staff vacuums the hallways. That's going to be fed by a house panel. That's what this is right here. So somewhere in each apartment building will be a house panel. And then in this case, there are two community panels, maybe one for the west side of the apartment complex, you know, inclusive of buildings A, B, and D, and one for the east side, inclusive of apartments C, E, and F. And each of these, of course, is going to have a meter. Well, that's all this is. It's just it's pretty complex, actually. It's both complex and complicated. But the question was, where's the equipment that regulates the inverter translating direct current to alternating current? Well, photovoltaic panels produce direct current. They produce direct current. And because almost all of our equipment plugs into the wall at alternating current, even though parentheses, a lot of our electronics run on direct current, but they get rectified back to direct current that's what that little equipment is, and that's what happens inside the TV or inside the computer, or next to, or in the box that you call a transformer, the transformer that's in the wire to your computer, right? So the big fat thing in your wire that looks like a pig that swallowed a python that swallowed a pig, the big bump there where you have a wire coming in and a wire coming out, that is a transformer that's taking 120 volt electricity, and it's stepping it down at maybe to 4 volts or maybe to 8 volts or 6 volts or something like that, so that your device, so that your computer or your iPad or your phone, when it's charging, can work. Now, here's a question for you. Why don't we just charge our TV? Why don't we just run our TV and our computer and our iPad on 120 volt alternating current? Why do we want to step it down to direct current that's like 4 or 5 or 6 volts? Why do we even want to do that? What's that equipment for? Go ahead and take a guess. So there's a bunch of reasons we want to do it. We do it because you know how silicon chips work. There's a bunch of wires that are like really close to each other, and if we start opening it up, and so we don't want shorts to jump across the wire. So we don't want 120 volts because there's conductors very close, and 120 volts is enough juice, enough voltage for it to possibly jump across. And also alternating current is a bunch of ons and offs, right? So 60 times per second, we're basically stopping the electrons and we're sending them back the other way. So we're going forward and then back, and then forward and then back, and then forward and then back. Well, to a piece of equipment, each time it goes forward and back, 120 times per second, each time it stops, it's basically turning off. It's basically turning off. So if it's turning off and on, if you know anything about computers, you know that that's all that computers are, just a bunch of switches that turn things off or on, binary switches, zeros and ones, bits and bytes. Ones means on and zeros means off. And so if we don't have direct current, if we have alternating current, it would be very difficult to get a signal through because of the alternating current would be confusing that signal that's trying to give us information. So what we're going to do is we're going to run it on direct current, and so it's being stepped down again. So there's all this back and forth between higher voltages and lower voltages and direct current and alternating current. But in any event, the power from the photovoltaics is going to come down here in direct current, and it's going to be connected to an inverter. And I don't think I have a photo of an inverter, but if you're at a computer, you can Google inverter, a photovoltaic inverter, and you can see it looks like a piece of equipment. It's usually mounted to the wall. It's about the size of a small like backpack, about the size of a backpack, and it looks like a panel. And what it's doing is it is inverting the direct current power that's coming from the photovoltaic and turning it into alternating current so we can feed it back into the rest of our system, because all the plugs are alternating current, all your toasters are alternating current. Your computer is, even though it's direct current in the computer, the thing that plugs into the wall is alternating current. And of course, the power company is alternating current. All right, good night, get licensed.